In this video, we'll be going through the 2021 Wave Systems paper. Question 1. Two loudspeakers are connected to the same signal generator, which is set to make the loudspeakers vibrate at a frequency of 8.95 times 10 to the 2 Hz, corresponding to a wavelength of 0.381 meters in air. The teacher makes sure that she wires the speakers so that they move in phase. A student uses her phone to measure the sound intensity at point A, which is equally distant from both speakers. She moves the phone towards B, noting that the sound gets quieter and then louder again. The diagram below shows the setup, not to scale. Determine the distance the student will have to move the phone to find the first quiet point between A and B. What we have here, of course, is a 2D interference pattern where we have lines of antinodes and also nodes between. Since we're asked to find the first quiet point between A and B, it's asking us to find the distance to this point here. Now our central antinode is an order number 0, and our first antinode is an order number 1. Our first quiet point right in between is an n equals 0.5. Let's look at what else we're given. We're given the separation between the speakers here, which is 1.5, and we're given the distance from our speakers to our observers, which is our L. Our distance here that we are trying to find is our X. And as you might have already guessed from the way I'm labeling these quantities, we're going to use this equation here. Where we have our D, we need to find our X, we have our L, we have our N, and I believe we have our wavelength upstairs, 0.381. We can start to solve this for X by multiplying both sides by L, and then dividing both sides by D, and I'm going to swap them around. Putting our numbers in gives me 3.175 meters, and since we're given 3 significant figures in the question, we'll round that up to 3.18. Explain how superposition causes the sound intensity to change when the phone is moved from A to B. The time has come, as it does in every Wave Systems exam, where we need to nail an explanation of 2D interference. So I'll launch right into it. As the phone moves from A to B, it moves from the n equals 0 path difference equals 0 antinodal line to the n equals 0.5 path difference equals 0.5 lambda nodal line. From here, it will move towards the n equals 1 path difference equals 1 lambda antinodal line. Antinodal lines are lines of constructive interference where waves meet in phase, resulting in a large amplitude. Nodal lines are lines of destructive interference where waves meet 180 degrees out of phase, resulting in zero amplitude. The sound intensity must therefore decrease to 0 as it moves from n equals 0 to n equals 0.5, then increase as it moves beyond n equals 0.5 towards n equals 1. Describe the difference in the pattern of loud and soft sounds the student would hear as they walk along AB if the speakers were further apart. Give reasons for your answer. Let's look back at the equation n lambda equals dx over L. Now, if we increase d and keep our lambda the same, and we look at the same order number line, we keep the distance to the speakers the same, what we must see is a decrease in our x to counteract the increase in d, in order for these to stay the same. In other words, as we move the speakers closer apart, the distances between the nodal and antinodal lines must decrease. Since n lambda equals dx over L, if n lambda and L are kept constant, an increase in d must cause a corresponding decrease in x. This means that moving the speakers apart will cause the antinodal and nodal lines, loud and quiet lines, to move closer together. The teacher also wants to demonstrate beats, with speaker 1 making a sound frequency of 8.95 times 10 to the 2 Hz. She connects speaker 2 so that it makes an equally loud sound of frequency 8.9 times 10 to the 2 Hz. Explain why the students hear a note that regularly changes in loudness, and determine the frequency of this beat. So as we get in every Wave Systems exam, we need to describe what beats are. As the frequencies differ, the waves move in and out of phase, causing alternating moments of constructive, loud, and destructive, quiet, interference. We call these beats. The frequency of these beats is the difference in the two frequencies. So to calculate our beat frequency, we just need to find the difference between these two frequencies here, which is just 5 Hz. Describe the changes to the frequency of beats the students will hear as the teacher slowly increases the frequency of speaker 2 from 890 Hz to 900 Hz. Speaker 1 remains at a frequency of 895 Hz. So let's visualize this. Now our speaker 1 remains at 895, whereas our speaker 2 frequency moves from 890 all the way up to 900. As mentioned earlier, the beat frequency is the difference between the frequencies, and so for starters, the difference is decreasing, and so the beat frequency is decreasing. At the point at which the frequencies match, there will in fact be a beat frequency of 0. No beats will be observed. Beyond this, as the frequency increases towards 900, we will once again hear beats in increasing frequency. And since the difference between each of these is 5, we're in fact going to have an equal beat frequency initially as we will finally. So let's put that into a paragraph. Initially, the beat frequency is 5 Hz. As speaker 2's frequency increases to 895 Hz, the beat frequency will reduce to 0. While both frequencies are the same, no beats are produced. As the speaker 2 frequency increases from here to 900 Hz, beats will once again be produced, an increasing frequency up to 5 Hz. Question 2. The speed of sound in air is 341 meters per second. Mark makes a sort of didgeridoo using a piece of plastic drain pipe 1.2 meters long. Mark vibrates his lips against the pipe, making the air vibrate in the tube and also blocking the tube at the end he is blowing into so that one end is closed while the other end is open. Calculate the wavelength of the lowest note that Mark can make with his didgeridoo. So if we imagine our didgeridoo with a closed end and an open end, the lowest note is going to be the first harmonic, which looks something like this. The proportion of a wavelength that is in the pipe is 1/4. If you think about a wave as being like that, what we're looking at here is really just this section here, which is 1/4 of the total wave. So that tells us that the length of the pipe is a quarter wavelength, or alternatively multiplying both sides by 4, the wavelength is 4L. We know the length of the pipe is 1.2, so that gives us 4.8 meters. Some of the richness in the tone of the didgeridoo is caused by the presence of overtones. In the space below, label the positions of displacement nodes N and antinodes A that the first two overtones will produce. And so our first harmonic has a node at the end, we always have a node at the end, and an antinode at the opening. Our first overtone, which is our second harmonic, of course still has a node at the end, as well as an antinode at the other end, but has an additional node within the pipe. Right here. Our second overtone, once again node at this end, antinode at the other end, will have 2 nodes within the pipe. So for our first overtone we have node, antinode, node, antinode. And for our second overtone we have node, antinode, node, antinode, node, and antinode. Once again, all equally spaced. State how the frequencies of these overtones relate to the lowest fundamental frequency of the pipe. For our fundamental frequency, the wavelength in the pipe is 4L. Since there is a quarter of the wavelength in the pipe, we need 4 of them to make a full wavelength. For our first overtone, you might see that we have 1, 2, 3/4 of a wavelength, or that the wavelength is 4/3 of the length, that we need 4 of these thirds to get a full wavelength. For our second overtone, if we split this up into our quarters, you might see that a wavelength is 1, 2, 3, 4 fifths of this pipe, since this here is a full wavelength. So now if we call this lambda here our fundamental lambda naught, our first overtone is 4L over 3, so it is lambda naught over 3. And our second overtone is 4L over 5, so it's lambda naught over 5. Now, because frequency is inversely related to wavelength, if the wavelength of our first overtone is 1/3 of the fundamental, then the frequency of our first overtone is going to be 3 times the fundamental. Similarly, if the wavelength of our second overtone is 1/5, then we must have the frequency of the second overtone as being 5 times the fundamental. Although Mark's lips vibrate at many frequencies, the pipe resonates only at certain frequencies. Explain how the sound waves travel in the pipe to produce only these natural resonant frequencies. First of all, we need to talk about how standing waves are produced in the pipe at all. We need to talk about the closed end and the reflection that occurs there. But also, we need to acknowledge that because this is a closed pipe, only odd multiples of the fundamental frequency will resonate. As you might see that we have our fundamental frequency, then the next frequency that's resonating is our 3 times our fundamental. The second overtone is 5 times our fundamental. And that continues. We would have our 7th times the fundamental, but what we wouldn't have is 2 times the fundamental and 4 times the fundamental. These cannot exist in a closed pipe. Sound waves travel from the open end to the closed end, where they reflect back 180 degrees out of phase. The incident and reflected waves create a standing wave pattern of nodes, destructive interference, and antinodes, constructive interference. Because this is a closed pipe, only odd multiples of the fundamental frequency are able to resonate, as even multiples cannot form with the required node at one end and antinode at the other. As Mark keeps blowing into the pipe, the air warms up, and so the speed of sound in the pipe increases. Explain how this will affect the resonant frequencies of the sound that the pipe produces. The relationship between velocity, frequency, and lambda is this one here. Now, the length of the pipe doesn't change, so that stays the same. But if the air warms up, the speed of the sound increases, as our question tells us. What this means mathematically is that our frequency must increase to match this. As V equals F lambda and lambda stays the same since the pipe length is constant, an increase in V must result in an increase in F. Question 3. Susan is watching a Formula 1 car race. As the cars go past, she hears the familiar sound of the engine change due to the Doppler effect. The speed of sound in air at the track is 341 meters per second. A car is approaching Susan at a speed of 44.4 meters per second, and Susan hears an engine at a frequency of 650 hertz. Show that the frequency that would be heard by the driver is 565 hertz. Our equation for the Doppler effect is this one here. And now, as the car is approaching Susan, it is going to be a minus down the bottom. As you've hopefully memorized by now, for an approaching source, this will be a minus, and for a receding source, it will be a plus. The frequency that Susan hears is our F prime, right here. We have the velocity of the wave, and we have the velocity of the source, 44.4 meters per second. What we're trying to find in this case is our F, which should be 565 hertz. So we of course need to solve this equation. The first thing I'll do is multiply both sides by the contents of the denominator, VW minus VS. And now I'll divide both sides by VW, and I'll also swap them around. Putting our numbers in, gives me 565 Hz, which can also be written as 5.65 times 10 to the 2 Hz, which is precisely what we're expecting. Explain why the motion of the car causes Susan to hear a different frequency to that which the driver hears. You may add to the diagram below to support your answer. Allow me to fix the drawing. And now if we were to draw our wavefronts affected by our Doppler effect, say we have a wavefront which has been produced with a center there. Now, since the car is in motion, the middle of the last wavefront produced is going to be offset. It's going to be behind where the current wavefront is centered on. So it's going to look something like this. And the same for the wavefront emitted before that, and so on. And so because these wavefronts are being produced offset to each other, the wavelength ahead of the car becomes shorter, which because the velocity is the same, our frequency is increased, and the opposite is true for behind our source. So let's now launch into our explanation of the Doppler effect. As the car is in motion, each wavefront produced is offset to the last, closing the distance to the wavefront ahead of the source and increasing the distance behind. This creates a shorter wavelength ahead and longer wavelength behind. Since v equals f lambda and v is constant, the frequency ahead increases while the frequency behind decreases. As the driver does not move relative to the source, they do not observe a Doppler shift and hear the true frequency. After the car has passed Susan and is moving directly away from her, Susan hears an engine frequency of 500 Hz. Susan wants to know whether the car is still travelling at 44 meters per second. By assuming that the true frequency of the engine has not changed, determine whether the car has changed speed. Let's take stock of what we have. We have our observed frequency. We know that the vehicle is moving directly away from her, which means that our plus-minus sign is going to be a positive. We are told to assume that the true frequency of the engine has not changed, which means that it must still be 565. And we can also safely assume that the velocity of the wave has not changed and that it's still 341 meters per second. Having all of this, we can now use our Doppler effect equation. Where we need to solve this for Vs to confirm whether or not it is 44.4 still. As with before, my first step is going to be to multiply both sides by the denominator. I'm now going to expand the brackets out. Subtract f prime VW from both sides, which, to save me a bit of space, I can factorise the VW out. And finally divide both sides by f prime. Putting our numbers in gives me 44.3 meters per second, which implies that Vs has decreased by 0.1 meters per second. Susan knows that as the car accelerates, the frequency of the sound produced by the engine increases. After the car has passed Susan, it accelerates away with an increase in engine frequency of 10%. When the car's speed has increased by 10%, will the frequency Susan hears be higher due to the higher revs or lower due to the Doppler effect? So we know that our initial frequency is our 565 Hz, and that our final true frequency, which I'll just call f, will be 565 plus our 10% of 565, or if you like 1.1 times 565, which gives me 621.5 Hz. As for the new speed of the source, well, we know that the original speed is 44.4, and that our new source velocity is going to be 10% more, so much like we did above, giving me 48.84 meters per second. Now let's figure out the final Doppler shifted frequency. For that, we can use our Doppler effect equation, where since the car is moving away, this is going to be a plus. Putting our numbers in gives me 544 Hz to 3 significant figures. So let's look at this in context. So before, as the car was moving away, Susan was hearing a frequency of 500 Hz. The question here is asking us that with the engine frequency increasing by 10%, but there also being an increased Doppler effect because there's a higher velocity, will the resulting frequency that Susan hears be more or less than 500 Hz? Performing our calculations, we've found it to be 544 Hz, which is an increase of 44 Hz over what Susan was previously hearing. And we're done.